Some physics problems here from Chapter 11. Our introduction to angular momentum. So number 29, we have two particles. Particle 1, an origin here. Particle 1 has a velocity in this direction. Call that V1. And what's the details? Particle 1 has a mass of 6.5 kilograms, and its speed is 2.2 meters per second, so we could find it's just regular old momentum by multiplying those together. And it's at a distance here, looks like it's r vector, right? Call that r1. They call it d1, I'm going to call it r1, 1.5 meters. And then the other one over here has a velocity, what's that, a mass of 3.1 kilograms. It's got a speed of 3.6 meters per second, and its distance, or its r vector, I'm going to call it r2, is equal to 2.8 meters. What are the magnitude and direction of the net angular momentum? So I think that the thing that may be the trickiest thing to realize here is that the net angular momentum, if you just find the RMV sine thetas, the sine thetas are both equal to 1 here. They're both at 90-degree angles, but they're going in opposite directions. So one of them's out of the page, one of them's into the page. And so we end up having to subtract them rather than add them. So let's do the angular momentum of the first one is equal to r1, m1, v1, sine of theta. It's at a 90-degree angle. But what's the direction of it? It's if I moved this r1 vector here so that they were like the hands of a clock, then r1 cross v1, I would have to go this way to get from r to v. And so if you're wondering how come I'm not going from r to p, the v vector and the p vector always go in the same direction. So finding r to v and r to p is the same direction. So I would have to go, I'd have to turn my hand upside down and go this way. So that's into page. That's into the page, which we could think of as like the negative direction. And then for the second one, if I move my r vector here, then to go from r to v, I would go this way. So it would be woo out of the page like that. So out of page. So if you got these two numbers, if you did this and added them together, you know, that's not a huge catastrophic mistake at this point, but it's important to realize that these two things are going in opposite directions. And you can see that if you're thinking about this in terms of rotation, although these objects aren't rotating, if they were rotating, this one's going kind of this way, right? That one's going sort of clockwise, and this one's going anti-clockwise, right? You know, that's what they say in jolly old England. They don't say counterclockwise, they say anti-clockwise. So here, if you want to see the numbers, this is the boring part. We have R, M, V, so that's 22.45. We're going to talk about the units, although they're easy to figure out. This is meters, kilograms, meters per second, so it's kilogram meters squared per second. Right? It's like regular momentum. If you think of it as r times p, it's like regular momentum, kilogram meter squared, times an extra meter because of the r. And then for the other particle, we have r, m, v. 31.25. So they're in opposite directions, so we would have to subtract them, and out of the page is winning. So 31.25 minus 22.45 would be 8.80 kilogram meters squared per second out of the page, or in the positive z direction, you could call it, or however you want to say that. I don't care how you name that direction, out of the page, in the positive z direction, whatever, as long as you realize you have to subtract those, that they're opposite directions, and that makes me pretty happy. That was number 29. Number 31. I suppose I should check to make sure that that's the right answer, but I'm pretty sure it is. So I'm sure you'll tell me if it's wrong. Number 31. We talked about in a little bit in class today, I think, that if you have here, if this ball's going up along this line, then when you're talking about the RMV sine theta, that this part, the r sine theta, is constant. That's this distance right here. Right, no matter where you are, if you're here, for example, here's your r vector, and then your mv or your v vector is going this way, then or up this way, then the r sine theta is the part of the r vector that's perpendicular to this. It's always this. It doesn't matter if it's here, 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 here. R sine theta is always that perpendicular part. And sometimes you even see this written like that, the perpendicular part of r, where we understand that this is r sine theta. So that makes this problem a whole lot easier, because p, that distance here, is 2 meters, and it's always 2 meters. So the r sine theta part is just 2 meters. So the angular momentum of this particle is always 2 meters times whatever its momentum is. And that might make you want to go back and redo it right now, which is a good idea. Turn the video off. Go do some physics. The mass of this thing is 0.40 kilograms. It's launched with an initial speed of 40 meters per second, a good clip. What's the angular momentum at the maximum height? When it's at the maximum height, the v is 0, right? Correct? Correct? V is 0. So that's 0. Halfway back to the ground. Let's see. I guess halfway back to the ground. How are you going to do that? I guess you could say, if we don't know what the maximum height is yet, I think we have to figure out what that is, right? So we can figure out what the velocity is when it's halfway back. So I guess we have to do a little kinematics problem. So if we're going to do the max height, that would look like this. So we've got a vertical problem where the acceleration is negative g. The final velocity at the peak would be 0. The initial velocity is 40 meters per second. And I would like to know, what is that maximum height? So Vf squared is equal to Vi squared plus 2a delta y, using that equation. Vf squared is 0. Vi squared is 40 squared plus 2 times minus g times delta y. So delta y is 40 squared divided by 2g. 40 squared divided by 2g. Right, you have to divide both of those or put it in parentheses, however you're going to deal with that. So maximum height's 81.6. I'm going to call that y max is equal to 81.6 meters. And they want to know what is the angular momentum when it's halfway back to the ground. So there's a couple ways you could do that. You could do it with energy now. since you know that the total energy, when it's at the top, that's the total energy, right? You could also say, oh, you know what? We could have done this with energy from the bottom, because that's the total energy. We could have just gone with half of that. That would have been much easier. So you could have said, well, look, so I'll show you both ways. And then how much kinetic energy does it have? Since we have two kinds, this is just translational, right? So it's mg delta y is equal to 1/2 mv squared. So when it goes, if you want to know what the v is, it's the square root of 2g delta y. And when it's dropped halfway back down from here, that v would be equal to the square root of 2g times half of this, which is what, 40.8? So that's the square root of 2g h. So it's 28.3 meters per second when it's halfway up. And then they wanted to know what's the angular momentum there. So the angular momentum would be equal to rmv sine theta, but the r sine theta part is 2, right? So the r sine theta part times mv is equal to 2 times the mass of the thing times the velocity, which we just found. So whatever that is, 0.8. So that's about 22.6 kilogram meters squared per second. And then thinking about that again, if you did energy considerations from the start, which I think would have been easier than this, you could have done, maybe you did do, and you were wondering why I did all that, you could say, well, the total energy at the bottom is just 1/2 mv squared. And when it gets halfway up, because gravitational potential energy just depends on h, and it's linear, right? It's just mg times h, which means half of it would be gravitational at this point. So that means the 1/2 mv squared, you'd only have half of that energy. So you could say the total energy at the bottom is equal to 1/2 mv squared, 1/2 mv squared, which is 1/2, oh, did I do, I had a bad feeling that I did something wrong here. I think I did. Hold on, let me just redo this real quick. 2 times, no, that's right, sorry, never mind. So 0.2 times 1600, so that'd be 320 joules. So with the kinetic energy when it's halfway up, it's only going to have half of the kinetic energy. And the reason is, again, because gravitational potential energy only depends on height. It's a linear multiple mg times the height. So that means half of it will be gravitational there, and that means only half's left for kinetic. So that would be, half of this would be 160 equals 1/2 mv squared. So v would be equal to square root of 2 times 160 times the mass, which is 0.4. I sure do hope we get the same answer here. Let's see, square root of 2 times 160 times 0.4 is not the same answer. Dang it. Let's see. Somewhere I did something wrong. Well, if that's the 160, if I did this right, then that potential energy at the halfway point, if that's right, should be the same. So mass times 9.8 times the halfway point would be 40.8. Yeah, that's 160, so that's right. What did I do wrong? Did I miss this? Half, 2. Oh, whoops. Sorry. Divided by the mass, not times mass. So that should have been the square root of 2 times 160 divided by 0.4. There we go. So it is the same. So anyway, a couple ways you could do that. And then I lost track of where we are here. Now they want to know what is the torque on the ball about point P due to the gravitational force when the ball is at maximum height and then halfway back to the ground. So remember the torque is equal to R times F times sine theta. And if you're thinking about that, oh, sine theta, right, we were doing that today. So actually the formal definition of torque, if you want to get into the vector thing, it's really equal to R cross F. Right, so it has the same kind of directionality into or out of page, which is consistent with all the other rotational stuff. So here, R F sine theta, we have, when it's at max height, remember the R sine theta part. R sine theta is just equal to 2 meters, always. It's the perpendicular part of that distance, so that's still true there. So R sine theta is 2 meters, so the torque at the top is equal to 2 meters times the gravitational force, which is mg. I don't know why I put units in there when I left them out there. So that's 2 times 0.4 times 9.8, which is 7.84 kilogram meters squared. So are the units for torque. Right? No, they're not. Units for torque is a force times a radius. So it's Newton meters. Sorry about that. That's units for I. Newton meters. And if you're thinking about, wait a second, then what's the torque anywhere? If R sine theta is always 2 meters, the gravitational force is always mg, so that means the torque due to gravity about this point is always equal to 7.84 Newton meters. So I think that's going to be the answer for part D also, once we realize that. So I think good to understand this, that the both torque and angular momentum have this nice property that if we're moving relative to a fixed point, the R sine theta part is constant. That sure is helpful to remember and understand. All right. Number 37. We've got, here we're looking for finding angular momentum of a rigid body rotating on a fixed axis. So in number 37, that rigid body is a collection of 3 particles. Looks something like this, where, let's see, the mass of each one is 0.023 kilograms. That's the mass of each of those. And the D, the distance here, is 0.12 meters for each. they're fastened to 3 rods of length 12 meters, and the rods have negligible mass, so we don't have to worry about the moments of inertia of the rods. So that means, let's just go ahead and calculate that I. The I of the whole assembly is just 3 particles, mr squared plus mr squared plus mr squared. So that's m. The r for the first particle is just 0.12 plus m. The r for the second particle is 0.24. And for the last particle would be 0.36. So just pop that out of the calculator. 0.023 times 0.12 squared plus 0.24 squared plus 0.36 squared. So we have a total rotational inertia of 0.00464 kilogram meters squared. Or you can write that in scientific notation if that makes you happy. They're rotating around point O with an angular velocity of 0.85 radians per second. And we want to know what's the rotational inertia of the assembly. I guess we just did that in part A. And B, the magnitude of the angular momentum of the middle particle, and then the magnitude of the angular momentum of the whole thing. So for the middle particle, it would just be, the angular momentum would be middle particle, that would be its I, times omega squared. I should write here, that's what I need to, I times omega, not squared, sorry, I omega. And then for part C, for the whole thing, that's just for particle 2. And then for the whole assembly, it would be I times omega for the whole thing. And since I have the I right there, I'm just going to do that now. So it'd be I times omega is 0.85, so that's about 0.0039, and then this is an I, which is kilogram meter squared times an omega, so kilogram meter squared second, right? Notice that's the same units as when we do L, right? The small l, that is. And then here, 0.023 times 0.24 squared. Just to compare, that's the rotational inertia of just the middle particle, smaller of course than that because that's all 3 particles, times 0.85. So this one is 0.0011 kilogram meter squared per second. That's pretty straightforward, I think. 3 particles, just add up their I's. The last one, 42. I picked this one for you to do because I like the idea of this graph. This is a graph of torque versus time. So if you're thinking about your non-rotational analogs, this would be like a graph of force versus time. And I hope that when you think about, or when you see a graph of force versus time, that puts you in mind of something. If you have a graph of force versus time, the area under that graph is equal to the change in momentum, right? That's impulse. Change in momentum is equal to impulse, and impulse is equal to the area under a force time graph. So that means the change in angular momentum of something is equal to the area under a torque versus time graph. All of our relationships hold up here in the rotational world. So let's see, the scale is set by that starting value is 4 Newton meters for torque. What's the angular momentum of the disk about the rotational axis at time 7 and time 20? And is it initially stationary? It is. So for part A, that means the change in angular momentum is equal to the integral from here. We're going from 0 to, we want to know at time 7. Right? So that would be equal to, the antiderivative here is L, so that's angular momentum at time 7 minus angular momentum at time 0, but they told us it starts from rest, so this is 0. So we just need to find that area. And we do that by looking at the graph. So what do we have? I'm just looking geometrically here. It looks like I have something that's a 4 by 2 rectangle. Right, that's that first rectangle. And then I have a trapezoid that has a height of 2 over 2, and then the 2, or the base if you want to think of it as that, and then the two different heights are 1, 4, and then 3 on the other side. That's the area of that little trapezoid. And I've got another rectangle that is 3 on the bottom by 3 high. All right, so that'd be 8 plus 7 is 15, plus 9 is 24. And we're talking about angular momentum here, so that's kilogram meters squared per second. Just doing that by area. And then B, we want to find also at time 20. So the change in angular momentum, talking about from 0 to time 20. So let's see, I already know I've got up to 7, I know that it's 24, plus, looks like when I go from 7 to 9, I have a triangle. I'm looking at the time axis here, so from time 7 to 9 I have a triangle, 1/2 base times height is 3. Then from 9 to 12, I have a triangle, 1/2 base from 9 to 12 is 3, times the height is, let's see, every block is a half, right? So 2, so the -3 is the height there, and these negatives are important, right, because that's negative area. Then I got a big old rectangle from 12 to 18, so that's got a base of 6, and its height is -3. And then last I have a triangle with an area of 1/2 base is the time from 18 to 20, and again the height is -3. I think that does it, right? So that's 24 plus 3 minus 4.5 minus 18 minus 3. So the 3's cancel, and I have 24 minus 22.5. So that's what, 2.5 kilogram meters squared per second. And again, I'm not making the fundamental mistake of calculus. I know that this really means L of 20 minus L of 0, but it starts off with an initial rotational angular velocity rather of 0, so that starts out at 0. And that is it.